So far, in our discussion on the topic of binary arithmetic, we have looked into the binary addition and subtraction in a fair amount of detail. Therefore, let us very quickly look at the next step of the binary arithmetic, the next feature, which is nothing but binary multiplication. So binary multiplication is probably one of the most simple binary procedures which you may encounter in arithmetic, even more simple than addition. So the rules are very simple. 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, and 1 into 1 is 1. These are the very simple rules of binary multiplication. There is no concept of a carry or a borrow whatsoever. Thereby, it reduces our problems or reduces our calculations by quite a bit. Now, having discussed the basic rules of addition, subtraction, looking at their some examples on how to use those basic rules, and now we know how to do binary multiplication. Very quickly, if you want to take a look at how to do a binary multiplication, it is this. Suppose I have something like 111 times 101. In that case, we will proceed in exact same manner as we do in decimal. This is a 0, so all of these will be 0. So we'll shift left by 1 bit, and then again we will have 111. So this will be 1, this will be 1, this is 1 plus 1, which means it's a 0 with a carry of 1. Again 1 plus 1 means 0 with a carry of 1. Here it is 0 with a carry of 1. So we can quickly cross check this. 111 is nothing but 7 and 101 is nothing but 5. And what is the answer? 1, 2, 4, 8, 16, 32. So this answer is nothing but 32 plus 2 plus 1, and that is nothing but 35, which is the answer. So binary multiplication is quite straightforward. If you know the basic rules of multiplication, all you need to know is addition. Now, having established these basic operations of addition, subtraction, multiplication, you can also do division by means of repeated subtraction. But I'll not get into that. You can try it out yourself. One of the basic questions which we now need to ask ourselves is, what is the relationship between these arithmetic operations and logical operations? When we say logical operations, we refer to those basic logic operations of and, or, not, and so on. The question now is that, can those mathematics have any kind of relation with the logic functions or the logic operations? So now it is time for us to very quickly come out of the mindset of a mathematician, take a step out of the mathematics that we've all been discussing so far, and take a look back at the logic functions. Although in one of the previous lectures, we have already taken a brief look at how the addition can be represented in terms of logic operations. So, therefore, let us quickly take a look at that again. Suppose I look at binary addition. Binary addition using logic functions. So we know the very basic rules of binary. Let us say I now want to have a system which accepts two binary bits, let us say A and B. Bits means digits. Each of them is of 1 bit. And then whenever you add 2 bits, we get always something called as a sum. And then we have something called as a carry. Let us say we have this system which is very simple looking, very straightforward. We have two inputs A and B, and we have two outputs, a sum and a carry. So therefore, let us write the truth table as we know quite well so far. So if I have two inputs A and B, I have two outputs, sum and carry. So 0 plus 0 means the sum is 0 and the carry is 0. 0 plus 1 means the sum is 1 and the carry is 0. 1 plus 0 means the sum is again 1 and a carry of 0. 1 plus 1 means the sum is 0 with a carry of 1. So now what we need to do is we need to express the outputs. One is sum, the other is carry, as some functions, let us say f1 and f2 of A and B. Looking at them very simply, we can see that sum follows the exact trend as that of a XOR, and the carry follows the trend as that of an AND gate. So therefore, the sum is nothing but A XOR B, and the carry is nothing but the AND A dot B. So therefore, the system can now be represented in this very easy manner. I have these two inputs A and B. I can use a simple XOR gate which looks like this, and the output is the sum, and the AND gate would be used for the carry. One thing to note here is that since I have used dots, these dots indicate connections, and two lines passing over each other, they don't indicate any connection. You can use dots like this. The other way to show them would be something like this, the jumper method, which shows that there is no connection. The technique or the procedure to show it, you can use any one of them you want, but both of these are acceptable practices. So don't be confused that this line and this line are crossing. It just does not mean anything. There is no connection. In some sense, you can think of this as two wires crossing each other on the breadboard, but physically not touching each other. So this is one way how to represent in the terms of logic gates. You can represent a simple 2-bit addition. Now this circuit, it has a very special name. If you notice, we had drawn a small block diagram in the previous page, if you recall, where there were two inputs and two outputs, which looks like this. So I have just drawn this dashed box to show that we can show the logic gates inside the box, and the outputs, the outputs and the inputs can be shown outside the box. Now this circuit, it has a rather special name. This circuit, it has a very special name. This circuit, which can add two binary bits, is called as a half adder. Now you may question, what do I mean by half an adder? It is still adding. Well, if there is a half adder, there has to be something called as a full adder. Yes, it is there. A full adder is a circuit that can add three binary bits. not just 2. So, the discussion on half adders and full adders, we are going to revisit. We are going to revisit them very shortly. And we'll be revisiting them at a time when we are in a position to understand them and their use completely, and how to deal with those kind of logic functions. So far, we have been largely limited to 2 variable truth tables as far as the lectures are concerned. In reality, there can be truth tables with more number of input variables. You can have 3, 4, 5, 6, and so on. So the question is that as the truth tables get bigger and bigger, our job as logic designers also become tougher and tougher. So therefore, we must know, or we must be in a position where we should not let that become too tedious. We must be in a position where we have the knowledge of certain tools and techniques which will help us attack those big looking truth tables. Mechanical manual operations can only take you so far. So we are going to come back to that. But for the time being, we will be content only with this. We are going to come back to this later. Now let us focus our attention to a very important question. That is on the foundation of this discussion. That is, okay, we are doing these arithmetic operations. We saw one simple example of this thing called as a half adder, where we can represent these arithmetic operations using logic gates. But let us not forget that the arithmetic operations and so on and so forth that is done by a computer or a processor, they are essentially based on electronics. Effectively, the computer has something called as a hardware. The hardware of a computer refers to the electronic circuits that it has. So, therefore, the more prudent question at this point of time would be, what is the basis for the underlying hardware? We know that yes, we can represent these arithmetic operations using logic gates. But what do we mean by logic gate? Yes, we know that logic gates are related to the way we think and make decisions. But that's okay for someone who is just into logic. But as an engineer, that is not sufficient. As an engineer, that is not sufficient. What we need to ask ourselves is that what is the circuit that is inside the logic gates? Can we represent logic gates using circuits? Because if we can, then we know that, okay, yes, we can definitely make our own logic gates using known circuits. We can implement those logic gates using our circuits. That leaves the freedom to the designer, to the engineer. And if needed, we can also make them work better in a way that which we want them to work. So, without further ado, let us then start the discussion on the electronics behind logic gates. Let us look at something which is very basic. Let us start with a basic gate. Let's say we have the OR gate. We want to implement an OR gate using simple electronic components that are known to us. Now, what are the simple electronic components that are known to us? resistors, capacitors, inductors, diodes, transistors. So the question is, using one or more of these known devices or these known elements, can we implement an OR gate? So before going to what an OR gate looks like, let us now convert our logic to voltages as we know it. We know that, let us say, high logic corresponds to a high voltage and low logic corresponds to a low voltage. So let us say, we had discussed this in a previous lecture. Let's just repeat it. Let's say logic 1 we will call as 5 volts and logic 0 we will call as 0 volts. Let us establish this convention. So therefore, in terms of voltages, if I write the truth table, normally OR gate has this truth table: A, B and Y. This is 0, 0, 0, 1, 1, 0, 1, 1. So the output would be 0, 1, 1 and 1. Now if we were to write this truth table in terms of voltages, let us assume that each logic variable, including the output, would have a certain voltage. So therefore, let us say VA, that is the voltage corresponding to the input A. We will also write VB and finally we will write VY. So therefore, when we have 0 volts, we want that the output should be 0 volts. Now when the inputs are 0 volts and 5 volts, the output should be 5 volts. When the inputs are 5 volts and 0 volts, the output should be 5 volts. And when we have 5 volts and 5 volts, the output should be 5 volts. So as we said, we have with us resistors, capacitors, inductors, diode, transistor. We can use one or more of these devices. If you want, you can use something else also. But for the time being, let us limit our discussion to these elements and let us say we have these available with us. And let us say these are all ideal. Let's assume we have ideal electronic components we have with us. Then, now the question is, so therefore we will need to make some kind of a circuit which has two inputs, let us say VA and VB, and one output, that is VY. How can we do this using one or more of these elements? So let us say we try to draw the circuit equivalent of VA and VB. So since VA and VB are inputs, we can assume that they are two voltage sources. Let us say they are DC sources. This I will call as VA. One more I will call as VB. Let us say they can take two values, either 0 volts or 5 volts. And somewhere, let us say over here, we will measure the VY with respect to ground. Because as you know from your basic electronics, all voltages are measured with respect to some reference terminal, and in most cases that is ground. So therefore, the question is, how can we realize an OR logic function? Let us keep things simple. If we use resistors only, can we realize an OR logic? Something tells me no. Because when you have 0 and 0, the output can be 0, no problem. But when one of these becomes 5 volts, then things are not so simple. We cannot connect these to each other because two voltage sources cannot be in parallel, which have different voltages. So therefore, the next best thing we can ask ourselves is that can we use something like a switch. Can we use something like a switch? Where if any one of the switches is on, then the output will be high. If you were to think of this as a very simple electronic circuit which has a battery and let us say a lamp. This is a lamp. Let us say I have two switches and switching any one of them on or at least one of them on would give me the lamp which will glow. So easily one way I can think of them is two switches in parallel. This is a lamp based logic. So I can say that this is A and this is B and the lamp is Y. So therefore parallel is something like OR, where any one of them is on and the output is available. So therefore neither resistor nor capacitor nor inductor can act as a switch. The easiest thing that can act as a switch is a diode. So therefore let us say we have ideal diode and let us say we connect two diodes in this manner. And then we connect them here and here. And finally, the output we observe across some resistor R. Let us say this diode is D1 and this diode is D2. This diode is D1, this diode is D2. Let us say both are ideal. What is the meaning of an ideal diode? An ideal diode is that diode which gets forward biased even with the smallest positive voltage across the PN junctions. So, therefore, one thing I can say is that when VA and VB are both 0 or 0 volts, in that case, the P side of each of the diodes, this is P, this is N, this is P, this is N. The P sides of both of these diodes are 0 volts and the N side is also indirectly connected to ground. So therefore, none of the diodes are forward biased. So if VA and VB is 0, neither diode is on. That should be very clear. Now let us take VA becomes 5 volts and VB becomes 0 volts. Now what will happen? If VB is 0 volts, that means D2 will still see 0 both sides. Let's say initially. If you assume that D1 is not there, D2 will again see 0 both sides. So therefore, I can say that with all certainty, D2 will also be off. But now VA becomes 5 volts, so therefore D1 gets a positive voltage at the P side. So therefore, since by default the voltage over here is 0, the diode becomes on and a current starts flowing. The diode is on. So it's like saying in this scenario, this VB arm is not there because this diode acts like a open circuit. So if this is not there, the second connection, the second line is not there, all we have is VA and a closed switch which is appearing across R. So if VY is taken across R, that means VY will be equal to VA. Because in this case, we are assuming that the diode is ideal and it does not consume any voltage by itself. So therefore, VY will be equal to VA, which will be equal to 5 volts. So far so good. Now what will happen in the reverse case? Suppose we have, let's say this is case 1, this is case 2, So this is case 3. VA is equal to 0 volts and VB equals to 5 volts. Now, both VA and VB arms are symmetric. So in this case, the D1 will be off now and the D2 will be on. Once again, it's like saying the top arm is not there. It's like an open circuit. So therefore, the voltage Vy across this resistor R will be nothing but this Vb, which is going to come over here. Because this diode D2 is ideal and it will act like a closed switch. So therefore, Vy will be equal to Vb, which is nothing but 5 volts. So far, so good. Now comes the interesting one, where both VA and VB are 5 volts. In this case, what is going to happen? In this case, what is going to happen? Well, in this case, both D1 and D2 are going to be forward biased. So therefore, we will indeed see VA and VB in parallel. Because now D1 and D2 will act like closed switches. D1 and D2 will act like closed switches. Therefore, in this case, what will happen is Vy will essentially see VA and VB in parallel. So Vy will be the parallel combination of these two voltages. Now, as I said, we have to be careful whenever we see two voltage sources in parallel. But the good part is that both sources are of equal value. So therefore, Vy will be equal to Vb, that is equal to 5 volts. Where both diodes, both D1, D2 are on. So what we see is that this is indeed satisfying our OR logic. This is OR gate using diodes. This is a very simple example through which you can make OR gate using diodes. Now, so far the discussion was very simple because we assumed that these two diodes, D1 and D2, are ideal. But as you know, ideal diodes exist in only one place, and that is nothing but the textbook. In practice, no diode can ever be ideal. So what is the difference between an ideal diode and a non-ideal diode? That is nothing but the junction potential or the built-in potential of the diode, which comes into picture when the diode is forward biased. So therefore, in reality, let us say when VA is 5 volts and VB is 0. Therefore, we can say that VA is like this. This is 5 volts. VB, it's like an open circuit. Doesn't matter. This is Vy. Now, D2 is anyway off, so we don't worry so much about it. Now, D1, when it is on, it will look like a small battery with its built-in potential. So therefore, this built-in potential or the V gamma of the diode, as the way it is normally represented, for silicon diodes, it could be generally around 0.7 volts. So in this case, what will be the Vy? The Vy will be nothing but 5 minus 0.7, that is 4.3 volts. So therefore, if you now were to write the truth table of the OR gate in terms of voltages, what you will see at Vy is not 5, but you will see 4.3. Now we have a problem. Although 4.3 is close to 5, it is not exactly 5. I would not have worried if this was 4.8 or 4.9. It is quite close to 5. But 4.3 could be a little troublesome. Why? Why? Suppose I have an OR gate. Let us say this is 0 and this is 5 volts. Then the output will be 4.3 volts. And suppose this is again feeding another OR gate. Now, whatever this other input is, I don't care. But then in that case, let us say, for example, if it is 0, let us say for just as a special case. Again, what will happen is that this 0.7 will come into picture for this gate. So this will be 4.3 minus 0.7, that is 3.6 volts. Again, if you have one more OR gate, the output will be 2.9 volts. This is disastrous. In a computer where you have multiple logic gates, hundreds and thousands of them, if you have such gates where there is such a big voltage drop, it is going to be disastrous. Now, as you see, 2.9 is somewhere close to the midpoint between 5 and 0. So therefore, this could very well be something like an unknown state. It's neither 0 nor 1. In that case, what will the computer do? This is disastrous. This is called as voltage fall or voltage drops. Therefore, this is a terrible, terrible, terrible circuit. It may look very easy to analyze, but in reality, this is just terrible. So some of the early circuits where there was not too much of complexity, what was done was that people used diodes. Yes, people used diodes. But they could not have very complex logic circuits. So therefore, if I want to keep the simplicity of this circuit, I want to use diodes, but I want to reduce this voltage fall. Then what would I do? Definitely one way is to reduce this. Can the built-in voltage of a diode be reduced? Can the built-in voltage of a diode be reduced? Well, it can be reduced if you change the material of the diode. This is normally the case for silicon diodes. If you go for germanium diodes, you will see that the V gamma is generally around 0.2 or 0.3 volts, which is better. So if it is 5 volts, the input, the output might be 4.8, which is still acceptable. But what's the drawback of a germanium diode? The drawback of a germanium diode is higher reverse saturation current. That is, it acts like a bad open switch when it is reverse biased. So therefore, in case of D2, when it is off, it might still conduct and a small current might still flow. Now you need to see what is the value of Is. If it is okay with you, you can go ahead. So therefore, all in all, it seems that although germanium is better, some problem may still arise. So therefore, all in all, what happened was in the few decades back, when people were trying to make gates out of circuit elements, they found that the utility of diodes are rather limited. Now, there must be some way to get out of this. But before we discuss that, let us see what if we had ideal diodes, what would an AND gate look like? What would an AND gate look like using ideal diodes? that would be, again we have two voltages VA, VB and an output voltage VY. So therefore, again we will have two voltage sources VA, VB, and let us say somewhere we will see VY. Now this is very interesting. This is very interesting. How can we use ideal diodes to get an AND gate? So therefore what we expect is that VY will be 5 volts only if both VA and VB are 5 volts. So therefore, let us sort of reverse what the OR circuit was. In the OR gate, the P side of the diodes was connected to the voltage sources. So here let's do the opposite. Let's connect the N side. And again, we'll connect them here. And let us also mirror the resistor which was earlier connected to ground. We will now put the resistor here, and here we will connect a 5 volt source or a 5 volt battery. Now let us see what will happen. If VA and VB, let's say this is D1 and D2, if VA and VB are both 0, what will happen? If VA and VB are both 0, the N side of the diode will see a 0 and the P side will see 5 volts. But remember, VY is always with respect to the ground. So in this case what will happen is that both diodes will be forward biased. So D1 and D2 will both be on. Therefore current will flow and VY will be nothing but the voltage it will see across ground. So therefore if VA and VB are both ground, all it will see is the diodes in parallel. So therefore this means VY is 0. Again, if we'll assume ideal diodes. Just to repeat, when both VA and VB are 0, both diodes are forward biased. Both diodes are forward biased and current will flow. Ideal diodes have 0 built-in voltage. So therefore the VY at this terminal and ground will only see the diode voltages, and these are anyway 0. So therefore VY will be 0. Now when either VA is 0 and VB is 5 volts, or VA is 5 volts and VB is 0, in either case one diode will always be on, one diode will be off. So therefore again using the similar logic we will get VY is 0, because the moment a diode becomes off it will have 0 potential, and that is what will come across. But when VA and VB are both 5 volts, then what will happen? Here also we have 5 volts, here also we have 5 volts. So therefore both diodes will be reverse biased. So D1 and D2 will be both off. So therefore it's like they are open circuits. Now no current will flow through this resistor R. So it's like saying whatever is this 5 volts, same 5 volts will come over here because the current is 0. So therefore in this case VY will be 5 volts. VY will be 5 volts. Once again, we have the AND gate where we have a high voltage only when both inputs are high. But using non-ideal diodes, which is a more practical scenario, what would happen? If we were to write the truth table, so therefore when the diodes will be on in case of 0, we will see something like 0.7. Again, it's not exactly same as 0. Here it would again be 0.7. Here would be 0.7. This would be exact 5 volts. This was for the AND gate. Remember what was for the OR gate? OR gate was just the opposite. This was 0, 4.3, 4.3, 4.3. So the OR gate is able to give you a good 0. And the AND gate is able to give you a good high or a good 1 logic. But these are called as weak 0. And these are called as weak 1. Okay. So therefore, because of weak zeros in the AND gate and weak ones in the OR gate, the diode based logic is not very good. The diode based logic is not very good. So we looked at two basic gates. That is the AND gate and the OR gate. Now what about the NOT gate? That's also a basic gate. The NOT gate, in fact, has one input and one output. So if I were to try and see what we can have for a NOT gate, we would have one input VA and one output VY. So what we expect ideally in the truth table is that VA and VY is there. So if the input is 0, the output should be 5 volts, and if the input is 5, the output should be 0. This is what we expect. So now, NOT gate is not so simple. Because using diodes, you cannot have something where, if the voltage increases at the input, the voltage will reduce at the output. That too with a single input. So are you aware of any circuit using those basic devices like RCL diode transistor? RCL diode and transistor. Using those devices, could we come up with a circuit that can act like a NOT gate, or where we can take the input, which when it goes high, the output will go low, or when the input goes low, the output will go high? Well, yes, we can use transistors. Suppose I have an NPN transistor, which looks like this. NPN bipolar transistor. Let us say I connect the emitter to the ground, and my input VA I am giving at the base through some resistor of the base. Some RB, let's say, so to speak. So I will have one resistor over here, which is RC, and a 5 volt source over here. And the collector is where I would measure the output VY. Now, let us say that the transistor has a beta or a current gain of 100. Let us say the collector resistor RC is 1 kilo ohm. And I want to now see what the input and output relation will be. Let us say RB would be somewhere about 100 kilo ohms. Let's just say what that would be. This is the example. Now let us say as an example, if VA is 5 volts, then the base current, which is nothing but the IB that's flowing into the base, would be nothing but VA minus the VBE divided by RB. That is 5 minus VBE, which is nothing but 0.7 volts, divided by 100 kilo ohms. that is somewhere about, I will just approximate it and say it is 45 microamperes. Roughly. It's actually going to be 43, but I'm just saying it as 45. In that case, the collector current, if you remember your transistor electronics, it's nothing but beta times IB. And beta is 100. So this will be 45 micro into 100, which is nothing but 4.5 milliamperes. So in that case, what will be Vy? Vy will be nothing but 5 volts minus IC times RC, because the collector current is going to be flowing this way. So IC is 4.5 milliamperes, RC is 1 kilo ohm. So this will be 5 minus 4.5, that is equal to 0.5 volts. So if the input is 5 volts, what I am seeing at the output is 0.5. Now, if the input VA is 0, then the base emitter junction becomes reverse biased. So the base current is 0, the collector current is also 0. So in this case, Vy will be exactly equal to 5. So therefore, what we are seeing is that after analyzing, the truth table comes out to be something like this. When the input is 5 volts, the output is 0.5 volts. And when the input is 0, the output is 5. This is called as RTL, or resistor transistor logic. It is little better because it's not exactly 0.7, it's 0.5. But still it is a weak 0. But it is giving a strong one. So, therefore, these are some of the conventional ways in which we can realize basic gates. However, modern days, the electronics has evolved so much that even the basic gates are not made using diodes or transistors anymore. They are made using some very special devices. And what that device is, or those devices are, we will see in the next lecture. Thank you.